Okay, in this video we are going to solve the problems from my notes. You need to know what is work. Work is the force in the direction of the displacement, this amount of force, not this one, the force in the direction of the displacement by the displacement. Fx delta x. If Fx is negative because the force is in this direction, if the force is in this direction, well, the Fx will be negative. Okay, so this is the idea of force. What force does? You can calculate the work by Fx delta x plus Fy with delta y. It will be the same thing that makes this operation, the force in the direction of the displacement by the displacement, Fs delta s. It will be the same that doing Fx delta x plus Fy delta y. So the work is the dot product of the force dot product by the displacement. The dot product is a number. Okay, for the work is measuring joules. When you have a force that is not constant, the total work will be the area the area behind the curve, because the small work will be the small displacement by the force. Force by the small displacement will be the work. The total work will be the sum of all these small areas, and this is how you calculate, for example, the work when the force is not constant, like the force of a spring that is a rectilinear line, is a force that is k by x. So the work is the area behind the curve. So this seen before, we have seen what you have as this. Everything that you have seen is here. Here is a good picture. This is the force. This is the displacement. The object is displaced through this trajectory. So the displacement is here. Here is the displacement. Here is at this distance the displacement. So you see the force in the direction of the displacement by the displacement. It's important to see that if this is the force, this one, this force is the sum of two forces, one in this direction and the other one up. This force is doing work. This force, the one that is perpendicular to the displacement, is not doing work. Okay, so this force only the force F sine of theta that is going perpendicular to the trajectory, this force only makes a change in the direction of the object. It doesn't make a change in the velocity. Then the change in kinetic energy is due to the force that is in this direction, in the direction of the trajectory. So this is the definition of kinetic energy that you already know, 1/2 mv squared. V is a number, it's an scalar. V squared is also an scalar, the magnitude of V, the definition. Of course, the kinetic energy is measured in joules. These are different ways of expressing the kinetic energy, 1/2 mv squared or 1/2 m v dot v. Oh, v dot v is the magnitude of the first by the magnitude of the second by the cosine of the angle. The angle that makes v with v is 0. Cosine of the angle is cosine of 0. Cosine of 0 is 1. So v scalar v is v squared, is the magnitude of v squared. Also can be done, can be written like p squared divided by 2m. P squared is mv squared. mv, everything is squared. M squared, v squared divided by 2m is 1/2 mv squared. So you can read this. So let's go, and this is the most important theory, the work, the network. This is the network. If there is only one force, well, it's the work of this force. It's the change in the kinetic energy. The work is the change in the kinetic energy, K final minus K initial. So K final is K initial plus the work. If the work is positive, K final will be bigger than K initial. If the work is 0, or there is no work when the displacement and the forces are perpendicular. If the work is 0, K final equal K initial, so the velocity will not change. If the work is negative, K final is less than K initial. The object loses energy, kinetic energy. Okay, let's go to see more things. Question. So this is the proof that the net work is the change in the kinetic energy. You see carefully, and you will see that Fx by delta x will be 1/2 mvx squared final minus 1/2 mv initial x squared initial, v squared initial. So this is the work, and you see a more general proof that the work in going from A to B is the change in the kinetic energy. So we have done this in class. You can see it again. So what we have seen is now this exercise. We have to place this exercise. What it say, this exercise? Say an object has velocity 10 meters per second. Okay, the object is moving with 10 meters per second. In what direction? I don't care in what direction. It has kinetic energy. It has 1/2 mv squared when m is 1 meters per second. When v is 1 meter per second and m is 1 kilogram. Okay, the object. What is the work done on the particle if the velocity is going to be 100 meters per second? So the object was moving at 10 meters per second. After some distance, not some time. In work we think about the distance displaced, not about the time elapse. Of course that there is time elapse, but we think about the distance is displaced. So after some distance, the velocity increases. So the kinetic energy increases. So the change in the kinetic energy is positive. Because the work is the change in the kinetic energy, what is the work done on the particle? The change in the kinetic energy. Let's go to calculate this. Okay, it's done here. The work is the change in the kinetic energy. So the work is the change in the kinetic energy. The mass is 1 kilogram. The velocity final is 100 meters per second. The initial velocity is 10. So the work is positive because you are adding energy to the object. And the work is, if you calculate, is around 5,000 joules. Okay. So this is an easy part. Let's go to the second part, what it say. The second part say, can you know what the force makes 5,000 joules? Well, no. We cannot know what the force that makes 5,000 joules because the force acting on the displacement, this will be around positive 5,000 joules. We know that the force have to be in the direction of the displacement. But who will make 5,000 joules? We don't know. We may be a force of 5,000 newtons acting on the distance of 1 meter will do 5,000 joules. But also a force of 1 newton acting on the distance of 5,000 meters will do also 5,000 joules. So we don't know what is the force, but we know that the kinetic energy has changed, so the work is positive because it has changed in a positive way. Can you tell me the distance traveled by the body? Well, no, I cannot tell. I cannot tell what is the distance. I can tell only that the force by the displacement, the force in the direction of the displacement by the total displacement is 5,000. But I cannot tell what is the force or what is the distance, the displacement. What it means that the object have kinetic energy. Okay, this is an interesting question. If you have kinetic energy, there is two things that can happen. If you have 5,000 joules, if you do a positive work, you increase the kinetic energy of the object. So what it means to have 5,000 joules? It means that you have 5,000 joules and you are moving with certain velocity v. So they have given you energy. They have placed the energy has flowed to the object. And how much energy has flowed? 5,000, maybe 1,000, 1,000, 1,000, and 1,000, and 1,000. Total 5,000 joules is here. It's kinetic energy. Kinetic energy. Now the object has this kinetic energy and can do something. It can release the energy to the environment, to the field, to the gravitational field, if it's in the presence of the gravitational field, or he can release the energy to a spring and compress the spring. He can do something with this energy. Let's say that there is a force acting on them that is a negative force. It's a force acting on the negative direction of the velocity. Let's say that the object is moving in this direction. In this direction. So if you add with a force like this, the work will be negative and you extract the energy from the object. So the object will lose energy. So the 5,000 joules will be 4,000 joules. You extract energy to the environment. 3,000 joules, you extract 2,000 joules now. You extract all the energy that they have, the 5,000 joules. So the 5,000 joules is not anymore on the object. It's on the environment. So what it means 5,000 joules at the beginning? It means that the object is capable. It has kinetic energy in 5,000 joules, and he can give the 5,000 joules to the environment, so the environment will have the 5,000 joules, and he will have nothing of kinetic energy, so his velocity will be zero. So 5,000 joules is the amount of energy that the object can release to the environment, the maximum total energy that he can release. The 5,000 kinetic energy is the total amount that he can release until he stops. And this is the answer. Okay, let's go now to see more. So please read a little bit of this. It says the same thing more or less. Let's go to now to see more what I have done here, So we are going to solve now this example. This is a very fundamental examples that you need to be sure that you understand. It says like this. A particle of mass m starts at rest and moves in a vertical distance in the presence of a gravitational field. So there is a gravitational field, there is a force, mg, going downwards, mg. This is the floor, and the object moves from y1 equal 10 to y2 equals 6. So the object moves this displacement going downwards from y1 equal 10 to y2 equals 6. Is the work positive or negative? Well, in going from the point initial A to the point final V, the work is positive because mg is in the same direction as the displacement. How much is the work? The work is the force in the direction of the displacement by the displacement. The force in the direction of the displacement is plus mg, is going in the direction of the displacement. And the total displacement is 4. From 10 to 6, there is a 4 meters displacement. So the total work is mg by 4. Pay attention. M is positive, G is positive, 4 is positive, total thing is positive, so the work is positive and should be positive because mg is going downwards and delta S is going downward, so the work is positive. So what the work is doing on the particle? The work is doing on the particle is to change his state of kinetic energy, change the kinetic energy. Then, if the work is equal to the change in the kinetic energy should be positive. So what is the work? The work is mg4 by 4. This is the amount of energy you place. You put the mass, you put g, and you put 4, and you obtain a number. So this number is the change in the kinetic energy. And the change in the kinetic energy is 1/2 mv squared at the position final. The position final is when y equals 6, minus 1/2 m, the position initial is when y equals 10. So if the initial position is 0, because they say that it's at rest, So this is v at the position y equal 10 is 0. So the equation that I will have is mg4 equal v squared at the position 6, at the final position. So v will be a square root of 8g, or square root of 80, or 9 by 9, 81, so approximately 9 meters per second. So he started at this point A with 0 velocity, and he arrived to this point with velocity a square root of 80. So the velocity is increasing, the kinetic energy is increasing, and the work is positive. So let's go to do the second part. The first part say find the work. The work is mg by 4. Find the work. Find the velocity. Oh, I already find the velocity. This is the velocity, 9 meters per second. Generalize the equation for any y. This is C. This is C. Generate the equation for any y. So the work is mg delta y. And the total work is the change in the kinetic energy, 1/2 mv final square. So v final square is 2g, the m disappear, so the 2 will go multiplication. 2g delta y is the final velocity. So delta y should be positive, because if delta y is not positive, how something square can be positive? So the final result is the 2, the velocity v is a square root of 2g delta y, being delta y equal y2 minus y1, no, because y2 is 6 meters, y1 is 10 meters, so this is minus 4. So the delta y is the magnitude of delta y. Now the work is the force in the direction of delta y. So you need to put the magnitude of delta y here. So this is the work, okay, and the work is the change in the kinetic energy. This is the change in the kinetic energy if the initial kinetic energy is 0. So now, with the absolute value, have sense this v. So delta y is the magnitude of delta y. So if it's positive, if it's negative, you have to consider the magnitude of this, and the magnitude of minus 4 is 4. And now it has sense. Find questions D. So we have generalized the equation. We have generalized the equation. This is the velocity at when he has displaced the amount delta y. Find the potential energy associated with this force. For every conservative force, there is a potential energy. In this case, the force is minus mgj. And we are going to prove that the potential energy, U, is mgy. This is what we are going to prove, that we already proved it in class, but we are going to prove it again in case that you have not get all the details. Okay, so the work done by the weight, because it's find the potential energy of the force of this force. So it's the work of this force. The work of this force is the force in the direction of the displacement. So now, going downwards, the work is positive because the force is positive, is going downwards, and the displacement is going downwards, so the work will be positive. Going downwards, y1 is bigger than y2. So y1 minus y2 is positive. So the work is the force in the direction of the displacement by the displacement. You see, y1 minus y2 is positive, so I can put with no fear y1 minus y2. So the work will be positive because this is positive and this m is positive and g is positive. So the work will be going downwards will be this expression. So what it said, our theorem say that the work is minus the change. Minus the change is u initial minus u final. U initial is u of y1 initial minus u of y2. What is the conclusion with this? The conclusion with this is that u of y1 is here, is mgy1. The minus sign is here, minus minus. mgy2 is here, yy2. So the conclusion is that u of y1 is mgy1 and u of y2 is mgy2. So the difference now, u of y1 minus u of y2 will be this minus this, mgy1 minus mgy2, or it will be this, mgy1 minus mgy2, this is this. So the difference is the same. So I have chosen the correct u of y. So the correct potential energy, u of y, will be mgy. This is u of y1 when y is y1. When y is y2, appear y2. When y is y, appear y. So u of y is mgy. So this is going downwards. It would be the same going upwards. It would be the same expression. You will see that it will be the same expression. So let's go to do the same problem, but going downwards to find the potential energy. So we choose the C. The C is a constant C that, if formally speaking, we have to add it because u of y1 minus u of y2, if I make the subtraction of this expression, the C will cancel. So any u of y1 will be valid because the C at the end will cancel. So it will have the same expression. So u of y in this is mg plus c. mgy plus c. Normally, what we do in problems is we choose u of 0 to be 0 when the y is 0. So if we choose u of 0 when y is 0, this will be 0, mg by 0, plus c. This fixes the constant c, because how you will solve this equation? 0 equals 0 plus c, so this say that c equals 0. So if you choose the floor to be the level of potential energy 0, then c is 0, and the expression, this one without the c, will take place. So let's go now to do it going up. The same calculation, you will see what's the logic of the same calculation. You will see that we will find the same expression. If we go up, then y1 is smaller than y2 going up. We go from an initial height smaller to a higher height. So y1 will be smaller than y2. So y1 minus y2 will be negative. What will be the work going up? Going up, the weight is going downwards. The displacement delta y is going up, so the work will be negative. What will be the work? The work, it will be the force in the direction of the displacement. Oh, but the displacement is going up and the force is going downwards. So this means that the force that I have to write is minus mg by the magnitude of the displacement. So I will write minus mg by the magnitude of the displacement. But the magnitude of the displacement is y1 minus y2. y1 minus y2 is negative because y1 is smaller than y2. So if I write the magnitude of the displacement, I should write here a positive quantity. mg, I cannot write y1 minus y2. I have to write the positive quantity. The positive quantity will be y2 minus y1. So the work will be minus minus plus mgy1 minus mgy2. Oh, and again, I have the same thing. This is equal to the change in the kinetic energy minus the change. So it's u of y1 minus u of y2. It's not u of y2 minus u of y1, because the work is minus the change. So this, again, is the same thing. U of y1 is mgy1, u of y2 is this, so u of y is this, mgy. So going up or going down, the calculation will be the same thing and will produce the same result. What result? If f is minus mg in the j direction negative, minus j, the potential energy U is mg by the height y. Okay, this is the potential energy associated with this force, and you have seen how I found the potential energy. So the part E say, establish the principle of conservation of mechanical energy. Mechanical energy is a number, and the total number is constant when the forces are conservative. And the mechanical energy is the sum of the kinetic energy and the potential energy. So how we will establish? The work is the change in the kinetic energy. Why we found the U? Because the change in the kinetic energy is minus the change in the potential energy. This equation is this equation. Delta K, the change in the kinetic energy, is K final minus K initial, minus delta U is U initial minus U F, minus U final. If you reorder, you will find this equation that is the conservation of mechanical energy, that say the number, the sum, will be constant. It will be the same sum at the initial. The mechanical energy initially will be the same mechanical energy at the final. Written in more detail, the Kf, the 1/2 mvf s squared, plus uf mgyf, the potential energy, final, equal the Ki, the initial kinetic energy, 1/2 mvi squared, plus ui mgyi. So this equation is the principle of conservation of energy applied to this problem. So you can find, given the initial velocity and the initial height, you can find the final velocity if they give you the final YF. So this equation is the equation of the conservation of energy for this problem. And you can use it and you can wonder, if the initial velocity is 3 meters per second and the initial height is 10 meters, what will be the final velocity when the final position is 2 meters? You calculate. It's just plugging numbers. Questions, let me see here. Okay, let's go to do more. Now let's go to solve this problem from my notes. It's a man moved vertically up an object of mass 5 kilograms at distance delta y plus 2 meters. So he's moving up, delta y is plus 2 meters with constant speed. With constant speed means that the magnitude of the velocity is constant. So if the magnitude of the velocity is constant, the acceleration is 0. So the problem is like this. He moved an object with velocity v equal constant, and of course he moved it at the distance delta y equal 2 meters. 2 meters. Hola, mi vida. So let's go to B. Okay, so the object is moving with constant velocity. The only way to move with constant velocity if it's the sum of all the forces are 0, because constant velocity means acceleration equals 0. So if the acceleration is equal 0, means that the sum of all the forces are 0. So now I want to emphasize that the change in the kinetic energy is due to the net force, to the force acting, the net force acting on the body. So because the velocity, the magnitude of the velocity doesn't change, means that the change in the kinetic energy is zero, so the work should be zero. So going downwards, there is the weight. Going upward have to be another force going up that should be equal to the weight going up. The magnitude of this force is the same magnitude of the force in this direction to produce zero acceleration, because the sum of all the forces will be zero, so the acceleration will be zero, and the velocity will be constant. It means that when the object displays up the 2 meters, there is 2 work here. The work done by the force 1, the one that is going up, plus the work by the force 2, this one, the force that is going downwards, that is the weight, mg. And the net force should be zero because the change in the kinetic energy is zero. So let's go to calculate each work and see that the sum should be zero. So how to calculate the work going up of the weight? We have done so many times that we can do it again. It's the force in the direction of the displacement, mg, by the amount of displacement, positive amount of the displacement. y2 minus y1 will be positive going up. So going up, the work is mg y2 minus y1, and this is positive. Wow. It's good, it's correct. This is the force of the force that is going up. The force that is going up is this force, mg. And the work is mg y2 minus y1. What is the force of this force, of the weight of the mg? The displacement is in this direction. So the work is the force in the direction of the displacement. So the force is minus mg, and the displacement is y2 minus y1. Oh, now the work is exactly opposite the work going downwards. The work of the force mg that goes downwards is minus the work of the force going upwards. You see, this is positive, this is negative, and the sum is zero. So now you can do the same thing going downwards, and you will find the same expression going downward. That will be y1, going downwards, y1 is bigger than y2. So y1 minus y2 is positive. So going downwards, this is the amount of displacement. It's a positive always, because the force, the work, is the force in the direction of the displacement multiplied by the quantity y1 minus y2 in this case that is going downwards. So let's go to calculate the work of this force, the force that have the magnitude mg but is going upward. What is the work of this force? I denote the work of the force going upwards like the work of this force going upward. It will be going from here to here. Going from here to here, the displacement is going in this direction, it's going downwards. The force is minus mg because it's in the direction of the displacement. It's in the opposite direction of the displacement, it's minus mg. Multiplied by the displacement. The displacement has to be something positive, so it's y1 minus y2. y1 minus y2. So this is the work of the force that is going up. The force that is going down is the weight mg. In going from here to here, the weight goes in the direction of the displacement. So it's plus mg, the force is plus mg, by the magnitude of the displacement. The magnitude of the displacement is y1 minus y2, because this is something positive. So the work of the force that is going downward is plus mg y1 minus y2 is positive. while this work is negative, the work of the force that is going upward. So in going from here to here, the total work is the work of the force that is going up plus the work of the force that is going down, that is the weight, and it will be minus mgy1 minus y2 plus the same amount mgy1 minus y2. So this sum is 0. So the work that one does in going from here to here, the work that this force that is going up is doing from here to here is negative, while in going from here to here, the work of the weight is positive, and the total work is 0. So the change in the kinetic energy should be 0. Okay, I think that I first finished the problem. Let me see the yes. So what is the work done by the man? The man does this force going up, do this force. So the work of the force going up is mgy2 minus y1. Going up, this is the correct expression because y2 minus y1 is positive, and the work of the force that is going up is positive. And this force, the force mg, do a negative work. Okay, so the work of the going up, the work of the force that is this one going up, of the applied force is positive, while the work of this one is negative, and going downward is the same thing, but it reversed this situation. When he was going up, this force a positive work. Now the work here is negative work, going downwards. Okay, so I hope you have catch this idea. Let's go more like this. So an object move, let's go to solve this example. An object moves from point A to point B. What is the work done by the normal force? The normal force is a force that is always perpendicular to the displacement. So if it's perpendicular to the displacement, cannot do any work because there is no projection of the force in the direction of the displacement. So the work will be 0. The work in going from here to here will be 0. The work in going from here, the normal force N, to here will be 0 because the normal force is perpendicular to the displacement. So there is no work. It means that the normal force cannot make a change in the kinetic energy. So what is the work done by the N? 0. What is the work done by the weight? Oh, okay. The work done by the weight is mgy1 minus y2. And here is again, the calculation is always the same expression. The work will be mgy1 minus y2 because the normal force will make a 0 work. So the net work is the work of the normal force that is 0 plus the work of the mg that is mgy1 minus y2. And the net work is the change in the kinetic energy. So if the question, the third question, I suppose it asks you, what is the speed at the point B? Well, you apply this equation. You can apply conservation of energy, of course, but this is the equation now. It's the same result, the same conclusion. The net work is the change in the kinetic energy. The net work is done by the weight, and the weight do a work that is mg y1 minus y2. And the net work is equal to the change in the kinetic energy. So if y2 is 0, this will be mg y1. And so the expression will be this one. If v1 is 0, this will be 0, so mg y1 will be 1/2 mv2 squared. So v2 will be 2 times g by y1. So v2 will be a square root of 2 times g y1. So what is the velocity? This one. This one is the same expression that we saw in another problem. we see the same problem again. So let's go to see what we have done here. Now let's go to see this problem. This problem say, you launch an object in the presence of a gravitational field, so there is the mg, there is g going downwards, and the object of mass m have a force that is mg going downwards. Okay, so we know that the objects that is being launched in the presence of a gravitational field constant will make a parabolic motion. It say, this problem say, find the work done by the weight in going from A to V. Well, the work done in going from A to V, let's go to do it in a different way. Maybe I have done the work done in using the dot products. You can check it here, but let's go not to go. Let me do it in another way, maybe. The work done is the force by the displacement. Maybe you can see these things in two different ways. Let's go to do it. So this is the trajectory of the body. This is the displacement, delta S. This is the mg. And the work done, we have said that is mg y1 minus y2. So y1 is this expression. And y2 is this height, y2. And the work done is mg y1 minus y2. So in going from here to here, will be mg y1 minus y2. So I'm going from A to V to C, let's go to put C, the work will be negative because y1 is smaller than y2. In going from C to D to B, this is V, the displacement is going in this direction, and the force mg is going in this direction. So the work in going from C to D will be the same expression. mg y initial, now is y initial is yc minus yv. Here is mg y0 or ya minus yv, and this is negative. But the work going from C to D will be positive. And the sum will be 0. The other way to say is like this. The mechanical energy at A should be equal to the mechanical energy at B. What is the mechanical energy at the point A? Is 1/2 mv0 squared plus mg y1 or y0 initial. And what is the mechanical energy of V? 1/2 mvv squared plus the potential energy mg yv. But what happened here is that the yv is equal to the y0. You see here that in the picture, this height is the same that the height here. Y0 is the same that yv. So applying conservation of energy, this will cancel with this because yv is equal to y0. So it will have one equation, 1/2 mv0 squared equal 1/2 mvv squared. So the only conclusion is that the v0 squared should be equal to the vv squared. So the amount of velocity, the magnitude, the speed at the point V is the same. Now it says find it's the same at the point A that at the point V. The amount of velocity, the direction of the velocity, no, the direction of the velocity at the point V is like this. But the length of these vectors is the same that the length of these vectors because the magnitude of V is the same. Find the work going from A to C. Okay, we apply conservation of energy. So the mechanical energy at A is equal to the mechanical energy at C. What is the mechanical energy of A? Kinetic plus potential, mgy. What is the mechanical energy at C? Kinetic plus potential, yc. Okay, what is the amount of kinetic energy? 1/2 mv0 squared. What is the amount of potential energy? mg y0, because y1 is the initial 1/2 mvc squared. And what is the amount of potential energy at the point C? At the point C is at the floor, so yc is equal 0. So this is 0. Okay, so I have this equation, equal this equation. I can cancel the m, of course. I can cancel the m, and I can arrive to this equation. So this is Vc squared equal V0 squared plus 2 times A delta Y. It sounds familiar, this equation? I think so, it's familiar. So, but it's obtained using principles of conservation of energy. So this is the velocity V of C. So if you want a practical problem, let's say that the y0 is 100 meters. Let's say that the magnitude of the velocity is 10 meters per second. So you launch the body and you want to find what is the amount of velocity when it arrives here, Vc. So Vc squared will be 10 squared plus 2 times g, the acceleration is g, 10, 2 times 10, by delta y. Delta y is the delta y is by y0. Y0 is 100. Sorry, here it should be written y0, not delta y. 2 times y0. Y0 is 100 meters. So the velocity Vc squared, if you launch a body like this, will be 100 plus 2 times by 10 is 20 by 100, 2,000, 2,100 meters per second. Wow. Wow. So the amount of velocity here is 2,100 meters per second. Let me see if I did the calculation correctly. A square root, sorry. Vc is a square root of this. Vc is a square root of 2,100 meters. Whatever it is, and let me see, 30 by 30 is 900, 40 by 40 is 4,000, 50 by 50, so it's 45 meters per second, around 45 meters per second. So he starts with a velocity of 10 meters per second in this direction, and he ends with a velocity of 45 meters per second in the tangent direction of the trajectory, but the amount of velocity is 45, and the amount of kinetic energy is 1/2 m45 squared. This is the amount of kinetic energy and at the point C, and the amount of potential energy at the point C is 0 because respect to the floor, the potential energy is 0. If there is something else, yes. Let's go. A mass of 2 kilograms goes up in a 30-degree inclined planes. At the point A, this is the point A, okay? This is the point A. The velocity is 2 meters per second. The mass goes up and returns to the point A with velocity 1.1. So at this point A, the velocity is 2 meters per second. The object goes up and later on goes down. And when he passes again through the same point A, the velocity is 1.1 meters per second. Find the work done by the friction force. How I will do this problem? I will say the net work is the change in the kinetic energy. The net work is the work done by the weight, because there is force that does work on the object, that is the weight, plus the weight of the friction, plus the work of the friction is the change in the kinetic energy. They asked me about the work done by the friction. The work done by the friction is negative because the friction is always, the force is always in the opposite direction of the displacement. So this amount should be negative. Is the change in the kinetic energy minus the work done by the weight. The work done by the weight in going from A up and again to A is zero because the height is zero. You go up, you do a negative work, the weight. You go downward and you do a positive, the weight, do a positive work. So the total work will be zero from going to A to, from A to A. From the same point, going up, negative work. Going downwards, positive work. Total work of the weight, zero. mg sine of theta is the work going up, but doesn't matter. So the work of the friction will be the change in the kinetic energy. So I know the mass, I know the final velocity, I know the initial velocity, 2 squared, so the work of the friction will be, if you make the calculation, like minus 3.79 joules, and it's negative as we have expected. The second thing say, if the coefficient of friction is 0.3, we know that the friction force is mu by the normal, mu sub k, mu dynamic. What distance can travel the mass until its velocity is zero? So what distance will go up until the velocity is zero? How we will do this problem? Okay, we will do the problem, write in the equation. What equation we will write? We will say, let me see here. We will say the net work is the change in the kinetic energy. The net work is the change in the kinetic energy. The net work is the work of the weight plus the work of the friction. The change in the kinetic energy is final kinetic energy when he's up on the inclined plane, the velocity is zero, minus initial kinetic energy, b0 squared. The work of the weight is always mg y1 minus y2. y1 minus y2, we have seen so many times that this is the work of the weight, and the work of the friction is negative, is mu by the normal. And this amount, the net work, is the change in the kinetic energy. And the change in the kinetic energy is minus 4. 2 squared is 4, 4 divided by 2, 2 by 2 is minus 4. Okay. So what is the result? The normal force is mg cosine of theta. So I will have, to solve this equation, we have to do the following thing. We have placed the equation mg y1 minus y2 equal minus mu by n. Oh, I think that I made a mistake. Okay, let's go to redo it. Don't worry. Okay, mg y1 minus y is the work done by the weight. The work done by the friction is negative. This one is also negative, of course, because it's the work going down by the weight that is going up, because y1 minus y2 is negative, so this work is negative. The work by the friction is negative, and this total work is the change in the kinetic energy. The change in the kinetic energy is minus 4. But this is not what I was doing. Oh my God, I'm so tired. Let me see. What we want to do is to find if mu sub k is the part B. Let's go to do the part B. The part B say, if mu sub k is 0.3, and the friction force, of course, is mu sub k by n. What is the distance that he can travel until he hits the velocity zero? So this is the inclined plane. This is the 30 degree. This is the object. The object is going from here to here. Here he has a velocity v equal 2 meters per second. On the top he will have a velocity v equals 0 because there are two forces that are acting on the body. in the direction of the displacement that are the weight and the friction. The weight is going downwards, but the force that is taking place here is mg sine of theta. So mg sine of theta is doing a negative work in going from this point, to the top. And there is another force that is the friction force that is going downwards and is also making a negative work. And the total work is the change in the kinetic energy. The total work is the work of the weight plus the work of the friction. The work of the weight, negative. The work of the friction, negative. The change in kinetic energy is 1/2 mv final square minus 1/2 mv initial square. V final, 0, because I go to the top. So the question that I will have is the work of the weight plus the work of the friction force will be minus 1/2 m by 2 square, because this is 0 is the final velocity. Oh, now I have to write the work of the weight. The work of the weight is mg y1 minus y2. Remember that y1 is smaller than y2. This is y1, this is y2. So y1 minus y2 is negative. So this work is negative. mg y1 minus y2 is a negative work. The work of the friction is mu by the normal by the displacement delta s that it happened. So the work of the friction is the force of the friction by the displacement, and it's a negative work. Okay, and this should be equal minus 1/2 m is 2 by 2 squared, so it will be minus 4. So I have two things that are negative. This is negative, this is negative, and the sum have to be minus 4. Let's go to do it. Let's go to do it. So this angle is 30 degrees. 30 degrees. So y2 minus y1 is delta s, the magnitude of delta s, by the sine of 30. Because y2 minus y1 is this distance. This is y2 minus y1. And delta s cosine of 30 will be this one, and delta s sine of 30 will be this one. So instead of writing y2 minus y1 equal delta s sine of 30, I will write y1 minus y2 minus delta s sine of 30. So the things will be negative. So it will be mg multiplied by y1 minus y2. y1 minus y2 is minus delta s sine of 30 minus mu. Mu is 0.3 by the normal. The normal is mg cosine of theta, cosine of 30. Cosine of 30 by delta s, by the magnitude of delta s. This is negative, and the total should be the change in the kinetic energy, that is minus 4, because it's a negative change in the kinetic energy. So delta S, the magnitude of delta S, that multiply. So let's go to put this equation like this. Let's go to change the sign. Instead of having minus, let's go to put plus. Plus mg delta S sine of 30 plus 0.3 mg cosine of theta by the magnitude of delta S equal 4. It's the same equation that the other one, but I have changed the sign. So what I will do, I want to find the displacement delta S, the magnitude of the displacement. So delta S, common factor, mg sine of 30 plus 0.3 g cosine of theta equal 4. So the delta S, the distance that he traveled on the direction of the inclined plane is 4 divided by mg sine of 30 plus 0.3 times g cosine of 30, cosine of theta, the angle theta. So this will be approximately 4 divided by m, to m is 2, g is 10, sine of 30 is 1/2, this will cancel, plus 0.3 by 10 is 10, and the square root of 3 divided by 2 is the cosine of 30. So this will be delta S will be equal 4 divided by 10 plus 3/2 is 1.5 by 1.7 is the square root of 3, and 1.5 by 1.7 is how much? 4 plus 1.5 plus 1 multiplied by 1.7. Let me take the calculator and I will do a better thing. 1.5 multiplied by 1.7. This is 2.55. 2.55, so it will be 4 divided by 12.55. So it will be approximately 4 divided by 12.55. It will be 0.3 meters. Maybe I do a mistake because I'm too tired. But I think, let me check it. Let me check. I think I didn't make any mistake. These two forces are negative. The change in the kinetic energy have to be negative, of course. No, I don't think I made any mistake. And G2, G 0.3. I think it goes 0.3 meters up on the inclined plane. Let's go to see if there is more thing here. How to obtain, if the force is this one, minus kxi, the potential energy U is 1/2 kx squared. I have done in another video, so you can do it if you want. I think it's finished. Just read, you can use the result also. Here it's done, okay? It's done. That's all.